this title of the paper is No Substitute for Functionalism, and it's available on arXiv, and I work as a postdoc at the Applied and Computational Mathematics Division at NIST Boulder and the Department of Physics at CU Boulder. So, let me kind of go right into it. So I think earlier this year or late last year, there was a paper by Hoel and Kleiner who introduced a substitution argument based on a model of experimental setup in the science of consciousness. Because I only have 15 minutes, I'll try and keep it short just to introduce there, because there's a lot of formalism that goes behind it. But, for the most part, I'll try and explain what the idea behind the formalism is that, in general, the experimental setup in consciousness science is that you have a physical system, and you kind of like a physical system P, and you're trying to do experiments, which is captured by some kind of like function called OBS, and from that you generate these data sets, O, and those can have parts from which you derive your prediction of a theory, which is referred to as OI, and there is a function or a correspondence that takes the data set from the observation space to the experience phase, which is the prediction of a theory. And then there are those that go from the inference function that kind of takes the data sets part that corresponds to inference and maps it onto the same experience space. So, this can be thought of as like, say, the prediction function might depend upon the state of the neurons in the system or something like that, whereas the inference reports can correspond towards getting the actual reports from our conscious subject. So under this model, and E is of course the space of experience. So under this model, they introduced the idea of falsification. Falsification of the theory of consciousness comes when you have the prediction of a model not matching up towards the inference of the model, which says the prediction says you're having one experience, whereas the report from the person is saying you have a completely different experience. And they say that, like, falsification by substitution is when you can actually have a physical system. A substitution is essentially a physical transformation. So you go from the physical system P to S of P, and you do this while you keep the inference data fixed. What that means is that pictorially, both P and S of P generate the same inference data indicated as OR and OR prime, and hence the inference drawn from it remains the same in the experience space, but the corresponding prediction data changes. There's OI and then there's OI prime, and correspondingly you have the prediction drawn from OI and OI prime map onto different things, EP and EP prime. As you can see, there's no overlap between the two. So if you can achieve a substitution, or if a substitution of this form exists, which keeps the inference content the same, but the prediction changes, then you have what is essentially corresponds to an OR substitution, and there's a falsification. Right. So Hoel and Kleiner then go forward and kind of indicate what the conditions for substitutions are. They put forward two conditions, one which is called minimally informative, which means that, like, this at least indicates that not all predictions are the same prediction, right? If a theory just says, no matter what state you have in the observation data, it's always the single prediction, then, that's not useful. So that's like a minimal criterion where there should be at least two different predictions. And then they make another statement that says that prediction and inference data are independent. And what they mean by that is that this kind of is related to what we were talking about before. You can have changes in prediction data OI without changes in inference data. So they mathematically formalize this. That's the statement. And the mathematical formulation is that there is some variation which maps a physical system P to a different part of the physical system, the same physical space, where you would have different prediction prediction data sets, OI and OI prime, but the inference data OR remains the same. This is very similar to what we had talked about before. And the idea is that under this definition of independence of inference and prediction data, you either have every single inference operation is wrong, or the theory of consciousness under consideration is already falsified. So theorem 3.10 is the main result from their paper. So the part that what this current work adds is that trying to like distinguish between how independence is like defined and how it's mathematically formulated. Even though independence is defined as having different OI, different prediction data, that does not necessarily mean the prediction content is different. That is, so you can essentially have two kinds of variations. You can have variations for which OI and OI prime are not the same, but and prediction prime are still have overlap. And then you can have those variations where OI and OI prime are not the same, but prediction of O and prediction of O prime are also not the same. If you notice, the type 2 variations are the variations that are actually prescribed in the original Hoel and Kleiner paper, whereas type 1 variations can also exist, right? So, so kind of like going back to their theorem 3.10 can be kind of treated as, if I was to translate it, it would be the idea that if inference and prediction data are independent under a type 2 variation, then either every single operation is wrong or the theory under consideration is already falsified, right? So what that kind of maps onto is essentially you could have two different kinds of variations, OI to OI prime and say OI to OI double prime. And those, all of them could maintain the same, those which within the circle that maintain the same OR and can maintain the same prediction are the ones that kind of fall into type 1 and do not lead to pre-falsification. And those which maintain the same OR but give you a different prediction, those are type 2 variations. So it isn't enough to just know that the prediction and inference data sets are independent. You would need to know the type of variation under which they're independent. So in the paper, there was a whole bunch of candidate systems that were put forward for substitutions. These included things like artificial neural networks, Turing machines, universal intelligence, and finite state automata. The artificial neural networks, you can think of it in the simplest case where if you have a multi-layered neural network, and if you thought of as just the outputs from the last layer from where you're taking out data for your inference for reports, and the rest of the middle hidden layers as the layers from which you're drawing your prediction data, then you can easily think of cases where you can maintain the input-output relationship. Hence, you're maintaining the same inference content, but you can manipulate the architecture of the neural network to a large amount, right? You can like add nodes, you can change the connections while still maintaining the same input-output relationship. And this would essentially be an example of substitution. But let me take back. This would be an example of a variation. So the question now becomes, what kind of variation are these, right? And the same kind of applies to finite state automata, where you can have finite state automata with feedback can be decomposed to those without feedback using a Krohn-Rhodes decomposition. So, it becomes a question of asking, it's not enough to just have these variations. You have to determine what kind of variations these are with respect to the theory you have. So, and kind of pointing out that the substitution argument is actually a generalization of the unfolding argument by Dorig and co-authors, which the original unfolding argument kind of implied pre-falsification of like causal structure theories like IIT. So, so a way to think about this with a very simple example, this is borrowed from Hansen and Walker, where I essentially just flipped the image that they have. So what this is that you have two physical implementations of a 3-bit counter. These are the actual flip-flop implementations. You can actually think of them as your P and S of P, and you kind of like look at them. You're looking at the states of the network, states of this physical implementation, and you are drawing out the different states. You can write out the actual like state in terms of the binary encodings. You have one binary encoding for implementation 1. You have a different binary encoding for implementation 2. And if you notice that, for example, if you look at the second state here, it's 1, 1, 0, it's 1, 0, 0, even though they have the same functional relationship, right? They both come from 0, 0, 0, and they go to a different state, but they correspond to different encodings. So you can actually come up with, like, you can think of this as two different combinatorial state representations. They simply differ in the encoding structure or the representation, but they both correspond to the same finite state structure, depending upon the input and output. Depending upon how many inputs went in and what the outputs were, they both correspond to the same higher level abstraction structure, right? So you can think of theories that operate at this level and theories that operate at the CSA level and theories that operate at the finite state level. Hansen and Walker's idea, or the point that they were trying to make, was they were trying to show that this is essentially, one is a feed-forward implementation and other is a feedback implementation. And if your theory of consciousness distinguish between these two systems based on only on the CSA representations, which only differ from each other based on the encoding, then that's all that you're capturing. Your measure is essentially capturing the difference in the encoding strategies and nothing else. So what we're doing is that, based on that kind of idea, we are actually introducing what we're referring to as a level 1 functionalism, where the framework is just defined by the actual functional states, which are defined in terms of their relationships to other states and the inputs, and they're independent of any encoding. They're also defined by their functional structure, which corresponds to the topological relationships or the map of the form, which has state at time t-1, input at time t gives you a state at time t and the next output. And the outputs, which are essentially can be a non-invertible function of the functional states. And for these kind of level 1 frameworks, you can always come up with like an abstraction function, which can take the encoded structure and convert them to the level 1 FSA picture. And the other thing to remember is, from the experimental point of view, you have these prediction functions, and these prediction functions ultimately only depend upon the functional state. You can always construct them to depend upon the functional state. If you had your prediction function that takes in the actual, if O corresponds to the actual data, which is dependent upon the encoding, then you can always break it down into an abstraction function, which produces the logical functional state, and then apply a more predictional function that operates at that level. So, and this is to kind of differentiate it from level 2 frameworks, which actually depend upon particular encoding or representations that are tied to the realization. So we kind of differentiate between level 1 and level 2 functionalism. Having said that, the main result, I'm almost done. The main result of this paper is that type 2 variations, the ones that actually lead to pre-falsifications, do not exist for level 1 functionalist frameworks of consciousness. I won't go through the proof here. It's pretty simple. You can do a proof by contradiction, where if you defined using the definition of a type 2 variation and equivalency of functional structures, that is those different CSA systems that have the same higher level functional structure as defined in a level 1 functionalist theory, for those kind of systems, no type 2 variations exist. Hence, these kind of functionalism pictures are immune from the substitution argument and are not pre-falsified. So kind of like reiterating what Turing et al. Mentioned in their paper, that ideas like the global workspace, higher order thought theory, and predictive processing are level 1 functionalist theories, and hence will not actually be affected by the substitution argument. Theories such as like causal structure theory, like IIT, which has a flavor of a level 2 functionalism in there, even though they're slightly different from functionalist theories, but they have a flavor of it, and they are pre-falsified. Finally, so the paper essentially kind of differentiate between how independence was defined in the original paper and how it's mathematically formalized, that actually leads to 2 types of variations. So results in Hoel and Kleiner's paper only hold for independence via type 2 variations. So in this work, we actually show a formal proof that type 2 variations actually do not exist for level 1 functionalist theories. I kind of started calling them level 1 and level 2 because I am actually pretty, I'm kind of ignorant about the philosophical literature. And then someone had to teach me that, I can also think of them as Roel was a realizer functionalism. And that's a good way to think about it. And I encourage people to go and read about those. I think of the most popular theories of consciousness, which include predictive processing, global workspace, higher order, and IIT. Only IIT is subject to these arguments. So I think a claim that most contemporary theories of consciousness has already been falsified actually does not hold. But I do think that these kind of models, it's a very useful step in formalizing these kind of ideas. And I think we need more work to refine these models. So I think, so those are my references, and I'm done. Thank you.